Section 8.2 is integration by parts. In this section, we're going to learn a new tool to help us integrate, and this particular tool helps us undo the product rule that we learned when we learned about derivatives in Calculus 1. Recall from Calculus 1, we said that the derivative of u times v was the first times the derivative of the second plus the second times the derivative of the first. Now if we integrate both sides of this with respect to x, so we integrate over here the dx of uv with respect to x, and then remember you can split up integration over addition and subtraction, so then we're going to write this as the integral of u dv dx with respect to x plus the integral of v du dx with respect to x. Over here on the right hand side, if you're taking the derivative of something with respect to x and then you're integrating that with respect to x, those opposite operations cancel, and then all you would be left with on the left hand side is u times v. And then over here the dx's cancel, and that's just the integral of u dv, and here the dx's also cancel, and that's just the integral of v du. If I want to get the integral of u dv all by itself on one side of the equal sign, I need to subtract this integral of v du from both sides. So we end up with uv minus the integral of v du is equal to the integral of u dv. Now that is this formula right here, and that's your formula for integration by parts. For integration by parts, if we're given the integral of a product u times dv, that is always going to equal u times v minus the integral of v du. A mnemonic that a lot of people use to remember the formula for integration by parts is that the integral of u dv is equal to ultra, violet, mega, voodoo. Now the ultra is for the u, the violet is for the v, the mega is for the minus sign, and voodoo just helps you remember that it's b du. Now what we're going to be doing in this section is looking at integrands where we have a product, and when we do that we're going to have to identify of that product which one of those things is u and which one of those things is dv, so that then we can use this formula. When you integrate by parts, again you need to figure out which one of the given is your u and which one of the given is your dv. Well, there's some general guidelines for choosing u, and so what I'm going to put here is an order for choosing u that works 98% of the time. So the order that we are going to use in this class for choosing u is if a logarithm is present in the integrand, that's the first thing I'm going to choose for u. So this is just your order for choosing u. The next thing, if there's no log, look for inverse trig. If there's no log, no inverse trig, the next thing that would be your u is algebra. No log, no inverse trig, no algebra, the next thing is just trig. And the last thing is just an exponential. So we use the mnemonic Li8 to help us remember that first we choose logs. If there's no logs, then we choose inverse trig. No inverse trig, then algebra. No algebra, then trig. No trig, then exponentials. And that's the order that we're going to use for choosing u. And like I said, it works about 98% of the time. So let's use all of that information to find the indefinite integral for the next few problems. Example 1 is the indefinite integral of x sine of x dx. Well, this is not basic form and it's not a u sub, so the only other tool that I currently have in my tool belt is integration by parts. And recall, integration by parts, I'm going to abbreviate integration by parts, tells us that if you're looking at the indefinite integral of u dv, that's always going to equal u times v minus the indefinite integral of v du. So I need to determine in this problem what is u and what is dv. Well, we use liate for that. The first thing we do is we say, do I have a log present in the integrand? No, the only thing in my integrand is x sine of x, so there is no log. Inverse trig? Nope. Algebra? Yes. I have something algebraic in my integrand. Since I have something algebraic, that will be my u. Now we make a table, and in our table we identify what u is and what dv is. So our u was x, and our dv is going to be everything that's left over, in this case, the sine of x dx. And then for my table, I know that from u to get to du, I need to find the derivative, and from dv to get to v, I need to integrate. Now let's find du. Well, if u is equal to x, the derivative of x is 1 dx. Now let's integrate. If dv is equal to the sine of x dx, if I integrate the sine of x, I end up with negative cosine of x. Don't forget the formula. The formula says that the indefinite integral of u dv is equal to uv minus the integral of v du, ultraviolet mega voodoo. So in this case, the indefinite integral of x sine of x dx is going to equal u. Well, u is x times v. Well, v is that negative cosine of x minus the integral of v. V is still negative cosine of x. And then du. Well, du is my dx. Cleaning this up, I end up with negative x cosine of x, and then minus a negative is a positive, the integral of the cosine of x dx. Well, can I integrate cosine of x dx? Yes, I can. That's basic form. So in the end, this is just going to equal negative x cosine of x, and the indefinite integral of the cosine of x is positive sine of x plus c. Let's look at number 2. Number 2 is the indefinite integral of 5x divided by e to the 2x dx. Well, remember, I said that integration by parts undoes the product rule. So the first thing I'm going to have to do for this is rewrite it as a product. I also noticed that it's not basic form and not a u sub. So again, I'm going to need to use integration by parts. But integration by parts requires a product. It requires u times v. To rewrite this as a product, I can write it as the indefinite integral of 5x times e raised to the negative 2x dx. Now I use liate to determine what u should be. Well, I don't have a log, I don't have inverse trig, but I do have algebra, so my u is going to equal algebra. If my u is equal to 5x, I'm going to go ahead and find the derivative. The derivative du would equal 5 dx. Everything that's left over is my dv, so my dv is my e to the negative 2x dx. Now I need to integrate that. So we can use a substitution to integrate that, but I'm also going to talk about what to do when your substitution is linear, because it's going to be helpful if we can do those without a substitution in the future. If I were trying to integrate this all by itself, the indefinite integral of e to the negative 2x dx, right now we might want to use a substitution for it. We would probably let w, and I'm using the letter w because I'm using the letter u somewhere else. So I would let w equal negative 2x, and then dw would equal negative 2 dx. Well, I don't have a negative 2 dx, I would divide by negative 2, and negative 1/2 dw would equal dx. And then we'd come back here and we'd say, well, this is just the indefinite integral of e to the w times negative 1/2 dw. We would integrate that and we would get negative 1/2 e to the w plus c, which in this case is just negative 1/2 e to the negative 2x plus c. What I want us to do to get there quicker is to notice that if the substitution was going to be something that is linear, so here our substitution was going to be something that is linear, all you have to do is think to yourself, well, it's going to work like an e to the u, and I know that the integral of e to the u is e to the u, so I know this is just going to be an e to the negative 2x. But I'm always going to have to multiply that by the reciprocal of the coefficient of the x term. Well, the coefficient of the x term, or that linear term, is negative 2, and the reciprocal of negative 2 is negative 1/2. Notice, negative 1/2 e to the negative 2x is exactly what I got here. But that's just a way to do it without having to use a substitution, and hopefully the more we do these problems, the easier it is for us to not have to do a substitution to get to those answers when the u that we would choose, or that substitution, is linear. All right, let's finish this problem off. We know that it's going to be u, which is 5x, times v, which is that, negative 1/2 e to the negative 2x, and then minus the integral of v, which is still negative 1/2 e to the negative 2x, times du, which is 5 dx. Remember, this is ultraviolet mega, the integral of vu du. Cleaning this up, we have negative 5x over 2 e to the negative 2x, and then minus a negative 1/2 times 5 becomes a positive 5/2 that we pull out of the integral, and then all we're left with is e to the negative 2x dx. Well, can I integrate e to the negative 2x dx? Yes, absolutely. We've already actually done that over here. We know that that is equal to, well, this is just going to be e to the negative 2x, but then times the reciprocal of negative 2, which is negative 1/2, and then plus c. Cleaning this up, we end up with negative 5x over 2 e to the negative 2x minus 5 over 4 e to the negative 2x plus c. And you can leave your answer like this, and you can enter it into WebAssign like this. The textbook, you'll notice, will factor things out. You do not need to do that for this class, but just to let you know that the book is going to factor. It's going to say, okay, well, between these two, my GCF, or my greatest common factor, is going to be a negative 5 over 4, and they're going to go ahead and put the e to the 2x back in that denominator. And when you factor out a negative 5 over 4e to the 2x, you would be left with 2x plus 1. And so the textbook is going to have this answer. But again, you can enter that answer into WebAssign and it'll mark it as correct. So I don't care which answer you give me on an exam or a quiz. Either answer is correct, but you don't need to factor if you do not want to.